So classified paper 6, and we have the topic that is acid, base, and salt. The question is, student investigate the reaction between aqueous potassium hydroxide with two different aqueous solution of hydrochloric acid, solution A and B. So two solutions are there for hydrochloric acid. They might have different concentration. That's why they named as solution A and B. And the same potassium hydroxide is used for both of these experiments. Two experiments were done. In the first experiment, what we did, a burette was filled with the solution A. So in a burette, we have unknown solution A. Some of a solution was run out from a burette so that the level of a solution A was on the burette scale. What is the reason why we run out the solution? So main reason is that, to remove the air from the jet. Like if this is a burette and this one is a nozzle or a jet, because when we fill the burette, we fill from the top. So when we fill it from the top, there might be some trapped air here. So there might be some trapped air present in this part. So how we can remove this trapped air? We just open, no, not to remove impurity, because what usually happen that when you fill up the burette, so because we fill it from the top, so there is a trapped air inside in this region. So as a result, when there is a trapped air, the volume of a liquid which is present here won't be accurate. So how to remove this trapped air? We just run down the liquid, we open the tap so the liquid will flow out and all the air will be removed from it. The measuring cylinder was used to measure 25 cm cube of aqueous potassium hydroxide. So we used measuring cylinder to measure 25 cm cube of aqueous potassium hydroxide and we transferred into a conical flask. So in a conical flask, we have KOH. For such questions, I prefer that you draw a rough diagram just to have a simple concept, like because you have to compare sometime which solution is more concentrated. So you just sketch, you have potassium hydroxide and how much potassium hydroxide is there, that is 25 cm cube. And the burette was, in the first experiment, the burette was filled with solution A of HCl. Then few drops of methyl orange indicator was added. So what will the color of methyl orange initially when we add, because methyl orange is added in a conical flask.
Yellow in alkali. Yellow in alkali.
So because we have methyl orange, so initial color will be yellow. But when we add an acid, when we add hydrochloric,
neutralization, it becomes orange.
so it will turn from yellow to orange. So initial color is due to the alkali and the final color is due to acid. Because initially in the conical flask, we have an alkali and then we are adding an acid. A solution A was added slowly from a burette into a conical flask while the flask was swelled. That is the main purpose of using a conical flask. Why we did not use beaker here in the bottom? Why we use conical flask?
We have to still it.
Yeah, we have to swell the mixture. Whenever you want to shake or swell the mixture, conical flask, it prevent the liquid. Otherwise, if you have a large, because in a conical flask, the opening is small as compared to that of a beaker. So if I swell the mixture in a beaker, it might spill as compared to in a conical flask. So that's why conical flasks are more effective for whenever you have to swell the mixture, and in titration, we prefer to use conical flask. And usually when we carry out this experiment, we use a white tile. What is the reason for using white tiles?
To detect the endpoint of the titration correctly.
So we can identify the color change of endpoint easily or color change easily. That's why white tiles are there. And whenever we read the burette reading, like burette, we look perpendicular, and usually the background we keep it white. What is the reason? Because so we can easily identify the level. Like we keep a white background and then read the scale and look perpendicular. These are certain things which are related to the titration. Now, in the first one, use a burette reading. Initially the burette was filled with initial. What is the initial and final burette reading? Initial, use a screen annotation. You can fill. What is the initial and final? So the initial is 8, okay, but don't write 8. Write 8.0. Even it's written 8, but don't write 8. Write 8.0. Why? Because it is accurate to 0.1 cm cube. So you should be precise with your reading. And then the next is 17, and the difference is, when you take a difference, is 9.9. So means how much HCl is needed? We need 9.9 cm cube of HCl to react with 25 cm cube of potassium hydroxide. That is in the first experiment. The next one, the conical flask was emptied and rinsed with distilled water. The burette was empty and rinsed with distilled water. Then the burette was rinsed with solution B. So why first we rinse with distilled water and then we rinse with
first to remove
Impurities.
any impurity, and then to remove water, like dehydrating agent.
Yeah, so first we remove, why we emptied and rinsed with water? To remove any trace of solution A. Like if any trace of solution A is there, that will be rinsed with water. And then why we rinse with the solution B? To remove any water left. That's why. And the question is why burette reading? Look, for a burette, we find how much volume is removed from the burette. So like for a burette, that at the top it is a 0 mark. And then at the bottom we have 50 centimeter, 50.0 cm cube. So when we open the tap, the levels start to decrease. So how much liquid is removed from the burette? That is the liquid which is added. So for our burette, we always read from top to bottom, because it shows how much liquid is removed from it. And in a measuring cylinder, like what if you was having a measuring cylinder? So in a measuring cylinder, we read from bottom to top, because it shows how much liquid is present in the measuring cylinder. So this is from bottom to top. This one is from top to bottom. Then a burette was filled with the solution B. So we did the experiment and we filled with solution B, and some solution of a B was run out. A measuring cylinder was used to measure 25 cm cube of potassium hydroxide. We transferred, and few drops of methyl orange were added, and until an indicator show a color change. What is the burette reading? Use screen annotation to complete. So what is the initial burette reading and what is the final? So final is 27.1, 2 and 3, and initial is 7.5. So what is the difference? $19.8. Okay. So solution B of HCl, for a complete reaction with 25, we need 19.8 cm cube of HCl for a complete reaction with the same KOH. Can you identify which solution of HCl is more concentrated? A or B?
A, because we need less volume there.
Yeah, that's
So
right.
the
A,
moles will be same. If the moles are same, we need less
same
volume, higher concentration.
Yeah, same number of the moles, but in a smaller volume. Like here, if I say potassium hydroxide and HCl, example, if in the conical flask we have 10 moles of potassium hydroxide and we need 10 moles of HCl for a complete reaction. These 10 moles are present in 9.9, and another one in solution B, the same 10 moles in 19.8. So it means smaller volume, more moles are there, so that solution is more concentrated, and this solution is less concentrated. Is it clear, the idea about the concentration of the two solutions?
Yes, sir, clear.
The next part, we have to indicate the color change as we did in the beginning. We discussed, like, because in the conical, it's always the initial color is always in the conical flask, and the final color is what should be there, what is added from the burette, that decides the final color. So initial color, it was yellow, as we mentioned in the beginning, that because there was an alkali, and the final it will turn into orange. So the color change is from yellow to orange.
Sir, orange because it had neutralized.
Yeah, neutralize, and practically what happened, some of the acid is there. Yeah, so acid is actually what happened practically when I say, where say you have potassium hydroxide, when you are adding an acid, you will never get an exact point where acid is completely neutralized potassium hydroxide. You will get a point where acid is a bit more than potassium hydroxide. So what will happen? First, we have potassium hydroxide. We are adding an acid, so all the potassium hydroxide used up, and then it will have extra quantity of acid. But we ignore that quantity of acid present because we assume that that is a negligible or a very small quantity which won't affect our result. But practically, acid is more there.
Happen with
What?
It can even happen with the correct title.
Yeah, even it can happen with a correct titer. That's I'm saying you cannot get 100% neutralization point. You will always get a point where acid neutralizes an alkali and then acid is more. Or you will get a point where alkali neutralizes the acid and alkali is more. The one which is added from a burette is more. So usually we assume that this is the point of neutralization, but practically it's acid. Practically acid is more. A small quantity of acid is more. That's why indicators show a color change. Otherwise, if it was neutral, the indicator may not have a color change at that point. Is it clear?
Yes, sir, clear.
Why it is yellow? Because you have to understand the concept that when methyl orange, when you learn the color of methyl orange, if you have alkaline solution, if you have alkali, it is yellow. And if you have acid, it will be orange. So in the beginning,
should be red in acid.
Yeah, red is there, but usually the color changes because we consider a negligible quantity is there, so it is orange is acceptable. So in the beginning, what will happen? We have yellow. Why yellow? Because of potassium hydroxide. And then we are adding an acid, a hydrochloric acid, so it neutralizes. So as the moment it neutralizes, you write red acceptable, you write orange, it is also acceptable. Orange is more appropriate compared to red.
But in this case, it will be orange. In other cases, we have to write red.
So before the starting titration, the experiment 2, the conical flask was rinsed with water. Explain why conical flask was rinsed with water. What is the reason?
To remove traces of a solution A.
Conical flask. So mainly conical flask, when we rinse with water, the main purpose is to remove the substances from experiment 1. It's about conical flask. Like you were having a conical flask, you use in experiment 1, and you want to use it in experiment 2. So why we rinse? So we want to remove the content of experiment 1. Like the things which were there left behind in experiment 1, that we remove. That's why it is rinsed with water. Any content which was there in experiment 1, we want to. Then a conical flask was not then rinsed with aqueous potassium hydroxide. State how rinsing a conical flask with potassium hydroxide changed the volume of solution B needed for experiment. Look, we were
The
having a,
volume will not be on the scale as there will be residue left if we add it or rinse
so
it.
like example, say we were having 25 cm cube of potassium hydroxide, okay, and we titrated with solution B, HCl solution B, which we use about 19.8 cm cube, and we carry out the reaction. But they're saying if we rinse this conical flask with potassium hydroxide, so if we rinse with potassium hydroxide, so amount of potassium hydroxide will increase. Because, for example, if I rinse with potassium hydroxide, so there will be some potassium hydroxide left in the conical flask, as it will stick to the wall of the container, wall of the conical flask. So if I have, like, I will not have 25 cm cube, I will have more than 25 cm cube of potassium hydroxide. So what will the effect of HCl needed for this experiment? I need more HCl or less HCl?
More HCl.
So if we rinse the conical flask with potassium hydroxide, so as a result, we need more HCl. Why we need more HCl? Because the amount of potassium hydroxide increase as we rinse with potassium hydroxide. Like there is a leftover potassium hydroxide and then we fill with 25. So total volume may not be 25, total volume might be 26. Example. So for 26 cm cube, you need greater amount of HCl as compared to 25 cm. Is it clear, this one?
Yes, sir, clear.
Yes, sir, clear.
Then deduce which aqueous solution of A and B. So we did like aqueous solution A, we need only 19.9 cm cube. Aqueous solution B, we need 19.8 cm cube for a complete reaction with 25 cm cube of QH. So which solution is more concentrated, A or B?
A.
A is more concentrated because
We will write less volume for same mole.
yeah. So for A, for 25 cm cube, QH is there in a conical flask, but we need only 9.9. Here we need 19.8. So which solution is more concentrated? We'll mention A is more concentrated, and why? Because we need a small quantity for a complete reaction. So when this reaction happen or occur, we need a small quantity of it. In part E, explain why experiment 1 and experiment 2 should be repeated. Why we should repeat the experiment?
For accuracy.
So we can find an average repetition. We repeat experiment, we can find average or make an experiment more accurate, or we can also identify the to increase, make it more reliable. That's also fine. So why we should repeat? So we will make it more reliable, or we can take average, or identify an anomalous result. Like maybe I skipped D part. Okay, which part I skipped? Okay, deduce how many times more concentrated. Yeah, okay, D2. How many times more concentrated the solution of hydrochloric acid was than like how many times more concentrated this solution of hydrochloric, like what is the ratio of concentration? If you check, like this was 19.9, this is 19.8. The ratio of the volume is 1:2. So the concentration ratio is like A is twice concentrated than B. Because if volume of B is double, so concentration is half. So you can
We
say,
can also write C in the ratio.
so how many times more concentrated hydrochloric acid was there? The other solution. So A is twice concentrated than B. How we work out twice? Because the volume ratio is 1:2. So concentration ratio will be 2:1. No, B is not twice, A is twice concentrated. Like A is having more concentration than B. Because the concentration formula, concentration is moles divided by volume. Because the volume of the B is double, so its concentration is half. Or for A, when we check, the volume of the A is half, so its concentration is double. Because they're inverse. One is in numerator, another one is denominator. So if I need, like example, if I'm talking about B I need 19.9. If I'm talking about A, I need 9.9. So when I compare the volume, I can say B is half concentrated than A, or I can say A is twice concentrated than B. That's the same answer. So A is twice concentrated than B, or B is half concentrated than A. Is it clear, this one?
Yes, sir. Clear.
Yes.
Then deduce the volume of a solution B. If we carry out, look, first when we carried out the experiment with potassium hydroxide, when we carry out, it was 25 cm cube of potassium hydroxide, and from the burette, how much solution B was needed? It was 19.9.
So it will be double.
It will be double. We need 19.9 cm cube of solution B for a complete reaction. Now they're saying if I repeat the same experiment with 50 cm cube of potassium hydroxide, like we double the amount of potassium hydroxide, now it's 50. So what volume we need for a complete reaction? So it will be double. So 19.9 multiplied by 2, that will be 39.8. Okay. It was 90, I think it was 19.8. I think 19.8, not 19.9. So 19.8 times 2, it will be 39.6. So this will be deduce the volume which we need. So we need 39.6 cm cube of B. And what is the reason for that? Because the volume of KOH double. So we need twice the volume of solution B for a complete reaction. Describe one change that could be made to the apparatus to improve the accuracy of the result. If you see
Using
They use
pipette
measuring
instead of
cylinder, so
measuring cylinder.
yeah,
we
so
can say use burette.
pipette is right term. Because reason is that because you are measuring 25 cm cube. So whenever there is a 25 cm cube, better
Okay.
mention pipette. If it was like any other volume, say 15 or 12, like 16.5, any other volume is there. But as you can see, we are measuring 25 cm cube. So for accurate measure of 25 cm cube, use pipette instead of measuring cylinder. What describe what effect using a large conical flask have on the result? Like for example, I'm not changing the amounts. We took
No
the
change.
so we, like example, we took
It will
25
be
cm,
same.
yeah, 25 cm cube of KOH in a small conical flask, and then we took a large conical flask and we took the same amount, 25 cm cube. Will it affect the result?
Less accuracy maybe.
No, about the total, the final volume.
It will get swelled anyway, so it doesn't matter.
Does not make the difference. So no effect. Why it does not make an effect? Because like if I'm using like a solution B was added, so you will need 19.8 cm cube here, and you also need 19.8 cm cube. So does not make difference because you're not changing the amount of, even for example, sometimes they ask if I warm the solution, will it affect the result in terms of amount needed?
No.
No,
No, it won't affect because
but reaction would be fast.
reaction will be faster, but the final amount won't change. It will only change if we change the concentration of the reactant or we change the amount of reactant. So using the concentrate, you only changing concentration or the volume of solution will affect the final result. Otherwise, it does not make any difference. Moving on to the next question, a similar question is there and related to the acid, alkali, and salt. A student investigate the reaction between the dilute hydrochloric acid and two different solutions of sodium carbonate. A burette was filled to 0 mark with a hydrochloric acid. So this time what we did, the unknown solution is in a conical flask. Like we have a conical flask using a measuring cylinder, we fill 25 cm cube of E. So unknown solution is in conical flask, and the known solution, the hydrochloric acid, which is we know, we use for both experiment. For experiment 1 and experiment 2, we use hydrochloric acid by using two different solutions. One is solution E, another one is F, of different solution of sodium carbonates. So this one is solution F, and we use HCl. The initial reading is 0. Use screen annotation to work out what is the total volume of hydrochloric acid for first experiment. Initial is 0. So write 0.0. So the first experiment we need 10.2. So the first experiment we need 10.2 cm cube of HCl for a complete reaction. Now we did the experiment and a few drops of thymopethylene was indicator was used here. Then we did the experiment refill, and we use a methyl orange. So in the big, again, the methyl orange is added. If I say what will the color change, like in the second experiment, this is experiment 2, this is experiment 1. Experiment 2, we use a methyl orange. What will be the initial color? Because alkaline solution, what is the color? It's the same thing. It will be yellow initially. And when you are adding an acid, what it will turn, it is acceptable. You mention orange, you mention red as the acid is added. The experiment 2, use screen annotation to complete. So we need 20.4. So if you work out, you need 20.4. Can you identify which solution is more concentrated, E or F?
Solution E.
Which is
Solution
more,
E with the 10.2 centimeter.
which solution is more concentrated, E or F?
E.
The correct answer is F. Why? Because you took 25 cm cube here and you took 25 cm cube here. For E, the 25 cm cube of E, this time the unknown solution is in a conical flask. So 25 cm cube of solution E, how much HCl is needed for a complete reaction? The known solution 10.2 cm cube of HCl. Before that, unknown solution was in a burette, but now in this question, the unknown solution is in a conical flask. And when you did with solution F, the same 25 cm cube of solution F, how much the HCl is needed, the known concentration of HCl, you need 20.4. So I need more HCl to neutralize this F as compared to E. So if I need more HCl to neutralize this unknown solution, it means F is more concentrated than E. Is it clear? So it depends on
Yes.
which one
Yes.
which one is known and which one is unknown. Before the previous question, the unknown solution was in the burette. This question, the unknown solution is the conical flask. So if I need more volume to neutralize that unknown solution, it means that is more concentrated. So solution F is more concentrated than E. Then we did the experiment. We emptied and rinsed with a distilled water, and solution F was poured. Using a burette reading, the experiment 3 is there. So what is the initial and the final burette readings? 33, 2.4, and the difference 30.6. Okay. Then what is the color change? The color change, it will be starting with a yellow and turn into orange or red, you can say. because methyl orange is there in experiment 2. Compare the volume of hydrochloric acid in experiment 2 and 3. Experiment 2, we took, it was 20.2, I guess, and experiment 3 was 30.6. Experiment 2, just a minute, let me confirm. Experiment 2 was, you have to compare, like you have to take a ratio. Yeah, 20 point, this was 20.2 and this is 30.6. When I take a simplest ratio, I divide by the smallest value. So I will divide both of them by 20.2. So this will be 1 and this will be 1.5. So it means the experiment, it's like it is 1 is to 1. Okay, it was 20.4. So I'll divide by 20.4, both of them. So 1 is to 1.5. So it means the volume used is 1.5 times the experiment 2. Like a volume used in experiment 3 is 1.5 times compared to experiment 2. Determine the simplest ratio of the volume, like compare the volume of hydrochloric acid and explain any difference. Like why we need different amount of hydrochloric acid, you have to mention the reason here. So what is the reason, or what might be a reason? Solution F is more concentrated, that's why you need greater amount of HCl. So compare the volume. Experiment 3, we need more volume. And what is the reason for that? Because F is more concentrated than E. That's why you need different amount of HCl, the same concentration of HCl, but different amount. The ratio of experiment 1 is to experiment 1 and experiment 2. Experiment 1, it was 10.2 and experiment 2 is 20.4. So ratio is 1 is to 2. Is it clear?
Yes, sir, clear.
Then what volume of a hydrochloric acid would be required if experiment 3 was repeated using thymolpethylene indicator instead of methyl orange?
There is a pattern for this in the page first
Yeah, the first page
start
actually,
of this question.
yeah.
They gave a pattern.
So if you check, like in the first one, here when we use thymolpethylene, we need 10.2 cm³ for a complete reaction. The 10.2 cm³ of HCl is needed for a complete reaction. And we identified that the concentration ratio between E and F, that is 1 is to 1.5. Like what is the ratio of the concentration for the two solutions E and F? When we worked out here, the ratio is 1 is to 1.5, like comparison ratio. Or so same thing for E. If we have like example 25 cm³ of E,
You can also take ratio between the amount of HCl needed in
yeah,
experiment 1 and experiment
that
2.
is I'm doing. That's the same thing I am doing. Like example, we have E and F, and we took 25 cm³ of E and F. For experiment 1, when we did the experiment 1, we need 10.1 cm³. When we did experiment 2, the ratio of the volume is 1 is to 1.5. That we work out. So in experiment 1, if I need 10.1 cm³ of E, in experiment 3, with time, this indicator, thymolpethylene, as the ratio of the volume is 1 is to 1.5, so I'll simply multiply it by 1.5. So 10.1 into 1.5, which is, because the ratio, the concentration ratio is 1 is to 1.5. Like if I need 10 cm³ of this, I need 1.5 cm³
Shouldn't
of the
we
other one.
take the ratio as 1 is to 2?
No, 1 is to 2 is for experiment 1 and 2. But experiment 2 and 3, because experiment 1 and experiment 2 are done with the same reagent. Experiment 1 was done with hydrochloric acid in solution E. Experiment 2 was done with hydrochloric acid in same solution E. And experiment 3 was done with hydrochloric acid in solution F.
But here in the question they ask the same solution but with different indicator.
Yeah, so the same solution but different indicator. So using a different indicator, the ratio volume will be 1 is to 1.5. So experiment 1, we took 10.2 C, like experiment, the ratio of the volume or the concentration is to 1 is to 1.5. How we identified that the ratio is 1 is to 1.5? Because when we did the methyl orange, when the methyl orange was used with solution E, which was 25 cm cube, and with solution F, which was 25 cm cube, how much HCl is needed? Here we need 20.4, and here we need HCl of 30.6. So what is the
But what if
ratio?
solutions E and F have different concentrations?
So E and
That
F
will
have different
also affect it.
concentration, but the presence of the indicator all makes the concentrations are different. Like concentration of F is 1.5 times concentration of E. That's why we need 1.5 times the volume. So this is done with a methyl orange. But now we are doing with another indicator, which is thymol pathylene. And the ratio should be 1 is to 1.5 for E and F, their volumes. This is 25 cm cube. This is also 25 cm cube that we added in the beginning. And here, when we did this experiment, we need 10.1. So how much F is needed? We just cross multiply, like taking ratio 1 is to 1.5. That's why it will be 15.5, 15.3 cm cube.